How do lumped parameter models work in system modeling? Imagine trying to understand a complex machine by breaking it down into simple parts. That's exactly what lumped parameter models do. They simplify complicated systems by treating certain properties as if they are concentrated in specific points or components. Instead of dealing with properties that change continuously across a space, these models assume all relevant properties like mass, stiffness, and damping are located at discrete points. This makes the math much easier to handle. In practice, a lumped parameter model looks at parts like masses, springs, and dampers. Think of a mass as something that stores kinetic energy, which relates to how fast it's moving. Springs store potential energy, which depends on how much they are stretched or compressed. Dampers dissipate energy, acting like shock absorbers, and relate force to velocity. When you connect these elements in a certain way, you can describe how the entire system moves and reacts over time. The key is that the model uses ordinary differential equations. These equations tell us how the system's variables change with time. For example, how a car suspension responds to bumps or how a robotic arm moves smoothly. Because the properties are lumped into these elements, the equations are finite in number, making calculations much faster and more straightforward. This approach is different from distributed parameter models, which consider properties that vary across space, like wave propagation or heat transfer. Those models use partial differential equations, which are more complex. Lumped models ignore effects that happen over large distances or at very high speeds, which is okay when the system's size is small compared to the wavelength or signal travel time. Mechanical engineers use lumped parameter models all the time. For example, when designing a vehicle's suspension, they model the shock absorbers and springs to see how it handles rough roads. In biomechanics, body parts are often simplified as masses connected by springs and dampers to study movement and forces. These models are also useful when combined with more detailed finite element models, which handle complex geometries. The main benefits are that they turn complicated systems into manageable math problems, reduce the need for heavy computation, and help engineers analyze and control systems more easily. They can also simulate interactions between different physical domains, like mechanical and electrical systems, using similar lumped elements. In system dynamics and control, these models form the foundation for predicting how systems behave, designing controllers, and optimizing performance. They capture the essential behavior without bogging down in unnecessary details. Overall, lumped parameter models work by turning a physical system into a network of simple, energy-storing, and energy-dissipating elements. This approach results in a clear, usable set of equations that describe how the system responds over time.